Neptune drifts at the edge of our solar system, the farthest of the major planets, a world so distant that it exists in a realm of perpetual dimness where the sun appears as little more than a bright star in an otherwise dark sky. It is the eighth planet from the Sun, positioned beyond Uranus in the outermost reaches of the planetary neighborhood, a place where the warmth and light of the inner solar system have faded almost completely, leaving only the cold emptiness of deep space. Neptune moves along its orbital path with a profound slowness, taking 165 Earth years to complete a single journey around the Sun, a circuit so long that since its discovery, the planet has only recently completed its first full orbit as observed by human eyes. The planet appears as a deep blue sphere when viewed through telescopes or in images captured by spacecraft, a rich azure color that gives Neptune an appearance of serene depth, as if you were looking into clear ocean water on a calm day. This beautiful blue hue comes from methane in the planet's upper atmosphere, a gas that absorbs the red wavelengths of sunlight while allowing the blue light to scatter and reflect back into space. The methane is present in small amounts, mixed with the hydrogen and helium that make up most of the atmosphere, but its presence is enough to paint the entire planet in this tranquil shade of blue, creating a world that appears peaceful and cool, wrapped in layers of soft azure cloud that extend deep into the atmosphere. Neptune is classified as an ice giant, similar to Uranus in composition and structure but different in many details. While the larger gas giants Jupiter and Saturn are made mostly of hydrogen and helium, Neptune contains a much higher proportion of heavier materials, substances that include water, methane, and ammonia existing under tremendous pressure in the planet's interior. These materials are called ices by astronomers, though they are not frozen solid but exist in strange high-pressure states, compressed into forms that would be unrecognizable compared to the ice we know on Earth. The core of Neptune likely contains rock and metal, but most of the planet's mass consists of these compressed ices, giving Neptune its character as an ice giant, a world fundamentally different from the gas giants that orbit closer to the Sun. The atmosphere of Neptune shows more visible features than Uranus, with clouds and bands that create subtle patterns across the planet's face. The clouds appear as lighter patches against the deep blue background, bright wisps of methane ice crystals that form in the upper atmosphere and drift along with the winds. These features come and go over days and weeks, appearing briefly before fading back into the smooth expanse of blue, temporary visitors in an otherwise uniform sky. The presence of these clouds gives Neptune a slightly more dynamic appearance than its cousin Uranus, though the overall impression remains one of calm, a world where changes happen gently and gradually. The winds on Neptune flow through the atmosphere at speeds that, if measured, would seem quite fast, yet when we think of them in the context of this distant world, they become simply another part of Neptune's quiet circulation, streams of gas moving steadily through the thin, cold air. These winds are organized into bands that circle the planet, driven by the combination of heat from the Sun and heat rising from Neptune's interior. Unlike Uranus, Neptune does generate significant internal heat, radiating more energy than it receives from the distant Sun, and this warmth helps to drive atmospheric motion, creating the gentle circulation patterns that organize the clouds into their subtle bands. Neptune is slightly smaller than Uranus but more massive, containing more material packed into a slightly smaller volume. The planet is still enormous compared to Earth, with a diameter nearly 4 times greater, and its volume could contain more than 50 Earths. The gravity at the cloud tops is slightly stronger than Earth's surface gravity, creating a substantial pull that holds the thick atmosphere in place and shapes the planet into a nearly perfect sphere, with only a slight flattening at the poles caused by the planet's rotation. If you're still awake, that's perfectly fine. Let your thoughts drift along with Neptune in its distant orbit, moving slowly through the outer darkness, a world wrapped in deep blue clouds, turning quietly at the edge of the solar system. The planet rotates once every 16 hours or so, spinning at a moderate pace that creates a day-night cycle in the equatorial regions, though the concept of day and night is subtle at Neptune's great distance from the Sun. The sunlight that reaches Neptune is so weak that even at local noon, the illumination would seem dim and twilight-like, far less bright than a cloudy day on Earth. The Sun itself would appear as a brilliant point of light, much brighter than any star but no longer showing the disk we see from our own planet, a reminder of the vast distance that separates Neptune from the source of warmth and light in our solar system. The distance from the Sun to Neptune is nearly 3 billion miles, a span so vast that light from the Sun takes more than 4 hours to travel this distance, crossing the solar system at its maximum speed to reach this remote world. At this distance, the Sun's warmth is negligible, providing only a tiny fraction of the heat that reaches Earth, and the temperature at Neptune's cloud tops is extremely cold, around -350 degrees Fahrenheit, similar to the temperature at Uranus and among the coldest places in the solar system. This profound cold affects everything about Neptune, from the chemistry of its atmosphere to the behavior of the ices in its interior. Despite the cold and the distance, Neptune has an active atmosphere with weather systems that form and evolve over time. Occasionally, large oval features appear in the atmosphere, regions where material is circulating in organized patterns, similar to storms but described here simply as weather features, systems where the atmospheric flow has organized itself into a temporary structure. These features can persist for months or years before gradually dissipating, their material mixing back into the surrounding atmosphere. The features appear as darker or lighter patches against the blue background, sometimes surrounded by bright white clouds of methane ice that form at their edges where gas is rising and cooling. The winds in Neptune's atmosphere blow primarily in the same direction as the planet's rotation near the equator, creating organized flows that carry clouds and weather features along with them. At other latitudes, the wind patterns become more complex, with different layers of the atmosphere moving at different speeds, creating shears and boundaries where interesting interactions can occur. The overall circulation is driven by the heat rising from Neptune's interior combined with the weak input from the Sun, creating a system that maintains itself over long periods of time, a gentle but persistent atmospheric motion. Neptune has a magnetic field, and like Uranus, the field is tilted significantly relative to the planet's rotation axis and is offset from the center of the planet. This creates a complex magnetosphere that wobbles and shifts as Neptune rotates, creating a dynamic environment that extends far out into space. The magnetosphere interacts with the solar wind, the stream of charged particles flowing outward from the Sun, creating a protective bubble around the planet and its moons. Charged particles become trapped in the magnetosphere and spiral along the magnetic field lines, creating radiation belts and contributing to auroras near the planet's poles. As we drift onward, we can think about Neptune's rings, which are faint and delicate, barely visible even in close-up images from spacecraft. The rings are made of small dark particles, similar to those around Uranus, material that reflects very little light and appears as thin arcs or complete circles depending on the distribution of particles. There are several distinct rings, each one occupying its own orbital path around the planet, separated by gaps where particles are less common. The rings are named after astronomers who contributed to the study of Neptune, a simple tribute to the work of those who helped us understand this distant world. The ring particles orbit Neptune in the planet's equatorial plane, circling the planet in narrow bands kept in place by gravitational forces and possibly by small shepherd moons that orbit among the rings. Some sections of the rings appear brighter than others, regions where particles have clumped together into arcs, creating concentrations of material that stand out against the darker surrounding ring. These clumps may be temporary features, forming and dispersing over decades or centuries, or they may be maintained by resonances with Neptune's moons, gravitational interactions that keep the particles gathered in specific locations. The rings of Neptune are thought to be relatively young in cosmic terms, perhaps only a few million years old, created when a small moon wandered too close to the planet and was torn apart by tidal forces, or when two moons collided and shattered into fragments. The particles that make up the rings will gradually spiral inward toward the planet or be lost to space, meaning the rings we see today are temporary features, beautiful but ephemeral, existing for a brief moment in Neptune's long history before they fade away and are gone. If you're still awake, that's perfectly fine. These gentle facts about Neptune are here simply to accompany you, flowing past like particles in the planet's faint rings, each one a small piece of information drifting quietly through your awareness. Neptune has 14 known moons, ranging from tiny irregular fragments just a few miles across to Triton, a large world that is one of the most interesting satellites in the solar system. Triton is Neptune's largest moon by far, much larger than all the other moons combined, a world that is comparable in size to Pluto and shares many characteristics with that distant dwarf planet. Triton orbits Neptune in a direction opposite to the planet's rotation, a retrograde orbit that is unusual and suggests the moon did not form alongside Neptune but was captured by the planet's gravity sometime in the past, pulled in from the outer solar system and bound into orbit around the ice giant. Triton's surface is covered in frozen nitrogen, a bright icy coating that reflects sunlight and gives the moon a pale appearance. The surface temperature on Triton is among the coldest measured anywhere in the solar system, around -390 degrees Fahrenheit, cold enough that nitrogen, which is a gas at room temperature on Earth, exists as ice on Triton's surface. This frozen nitrogen creates a landscape of plains and ridges, smooth areas and rough terrain, a world that appears geologically young despite its ancient origin. The most remarkable feature of Triton is the presence of geysers, plumes of nitrogen gas that erupt from beneath the surface and shoot material high into the thin atmosphere. These geysers are thought to be driven by a process where sunlight penetrates the translucent nitrogen ice and warms the material beneath, causing the nitrogen to vaporize and build up pressure until it breaks through the surface in a gentle eruption. The plumes rise several miles above the surface before the material falls back down, creating dark streaks on the ice where the ejected material has settled. This activity shows that Triton is not a completely dead world but has processes ongoing even in the extreme cold of the outer solar system. Triton has a thin atmosphere, made mostly of nitrogen with traces of methane, a delicate envelope of gas that extends a short distance above the surface before fading into the vacuum of space. The atmosphere is so thin that it would be considered a near vacuum by our standards, yet it is substantial enough to affect the Moon's surface, creating winds that can move small particles and transport material across the landscape. The atmosphere may vary with the seasons, thickening or thinning as different parts of the surface are heated by the distant sun, creating a slow cycle that plays out over Triton's long year. The surface of Triton shows evidence of past geological activity, with features that suggest the crust has been reshaped by internal processes. There are regions called cantilever terrain, areas covered in dimpled pits and ridges that give the surface a textured appearance unlike anything seen elsewhere in the solar system. These features may have formed from the melting and refreezing of subsurface material, or from the collapse of surface layers, creating the unusual patterns we see today. Other parts of Triton are smooth, covered in frozen plains that show few impact craters, suggesting these areas have been resurfaced relatively recently in geological time. Triton's orbit is slowly decaying, meaning the Moon is gradually spiraling inward toward Neptune. This process is driven by tidal interactions between the Moon and the planet, forces that remove energy from Triton's orbit and cause it to shrink over time. Eventually, in the far future, many millions of years from now, Triton will move close enough to Neptune that tidal forces will tear the Moon apart, creating a new ring system around the planet from the fragments of the destroyed satellite. For now, however, Triton continues its retrograde orbit, moving steadily around Neptune, a captured world from the outer solar system now bound to the ice giant. The other moons of Neptune are much smaller than Triton, irregular in shape and dark in color, small rocky worlds that orbit the planet in a variety of paths. Some orbit close to Neptune, moving among or near the rings, while others travel in more distant orbits, taking months to circle the planet. The largest of these smaller moons is Proteus, an irregularly shaped object a few hundred miles across that orbits just outside Neptune's rings. Proteus is heavily cratered, marked by impacts from the early solar system, and it shows no signs of geological activity, a quiet frozen world that has remained largely unchanged for billions of years. Slowly, as we drift onward, we can think about the discovery of Neptune, which came about through a combination of mathematical prediction and observational astronomy. In the early 1800s, astronomers noticed that Uranus was not moving exactly as predicted by gravitational theory, suggesting that another planet beyond Uranus might be influencing its orbit. Mathematicians calculated where this unseen planet should be, and in 1846, astronomers turned their telescopes to the predicted location and found Neptune, a triumph of theoretical prediction and careful observation. The discovery showed the power of mathematical physics to predict phenomena that had not yet been observed, confirming our understanding of gravity and orbital mechanics. For more than a century after its discovery, Neptune was studied only from Earth, a small bluish disk that showed little detail even in the best telescopes. Astronomers measured its orbit, discovered its largest moon Triton, and noted the planet's deep blue color, but Neptune remained largely mysterious, too distant and too small to reveal much about its atmosphere or internal structure. It was not until 1989 that a spacecraft finally visited Neptune, providing the first and so far only close-up views of this remote ice giant. The spacecraft was Voyager 2, the same probe that had visited Jupiter, Saturn, and Uranus on its grand tour of the outer solar system. Voyager 2 approached Neptune in August of 1989, flying past the planet and Triton, taking thousands of images and making measurements of the magnetic field, atmosphere, rings, and moons. The encounter was brief, just a few days of close observation as the spacecraft sped past, but it provided a wealth of data that transformed our understanding of Neptune and its system. The images from Voyager 2 showed Neptune's deep blue color in vivid detail, revealing clouds and atmospheric features that had been invisible from Earth. The spacecraft discovered several new moons, all small and dark, orbiting among the rings or in more distant paths. It studied the rings directly for the first time, confirming their existence and measuring their structure and composition. The spacecraft observed Triton in detail, discovering the geysers and mapping the surface, revealing the cantaloupe terrain and the bright nitrogen ice that covers much of the Moon. The magnetic field was measured, showing its tilted and offset nature, similar to Uranus but with its own unique characteristics. If you're still awake, that's perfectly fine. Let these thoughts about Neptune drift through your mind, gentle and undemanding, a slow stream of information about this distant ice giant, the farthest major planet, wrapped in deep blue clouds, attended by its captured moon and faint rings. After its encounter with Neptune, Voyager 2 continued outward, leaving the realm of the major planets and heading into the space beyond, carrying messages and images from Earth on its golden record, a time capsule meant for any future civilizations that might encounter the probe in the distant future. Voyager 2 is still functioning, sending back data from interstellar space, though its power is slowly fading and eventually the spacecraft will go silent, drifting forever through the galaxy, a silent ambassador from our world. The data from Voyager 2 remains the most detailed information we have about Neptune, and no spacecraft has returned to the planet since. There have been proposals for new missions, orbiters that could study Neptune and its moons over multiple years, but the great distance and the long travel time make such missions challenging and expensive. For now, Neptune continues to be studied from Earth, with modern telescopes observing the planet in different wavelengths of light, tracking clouds and atmospheric changes, measuring the properties of the rings and moons, gradually adding to our understanding through patient long-distance observation. The distance from Earth to Neptune varies as both planets move in their orbits, but at its closest, Neptune is still nearly 2.5 billion miles away, a vast span that places the planet far beyond the reach of casual observation. The journey for a spacecraft to Neptune takes years, requiring careful planning and the use of gravity assists from other planets to reach the necessary speed. The weak sunlight at Neptune means that solar panels are ineffective, requiring spacecraft to use nuclear power sources, adding complexity and cost to any mission. Despite these challenges, Neptune remains an object of scientific interest and curiosity. As an ice giant, it represents a class of planet that appears to be common in the galaxy, with many exoplanets discovered around other stars falling into this category. By studying Neptune in detail, we can learn about how ice giants form and evolve, how their atmospheres behave, and what their interiors are like, knowledge that can be applied to understanding the thousands of similar worlds that exist around other stars. Another quiet detail is that Neptune is invisible to the naked eye, too faint and too distant to be seen without a telescope. Even through a telescope, it appears as a small bluish disk without visible features, requiring careful observation and good seeing conditions to appreciate. The planet's faintness and remoteness make it less accessible to amateur astronomers than the brighter planets. But for those who seek it out, Neptune offers a connection to the outer frontier of the solar system, a glimpse of a world that exists at the edge of our planetary neighborhood. The name Neptune comes from Roman mythology, the god of the sea, a fitting name given the planet's deep blue color that recalls the appearance of ocean water. The name continues the tradition of naming planets after mythological deities, and it has been used since the planet's discovery in the 1800s. The moons of Neptune are named after various sea gods and nymphs from Greek and Roman mythology, following the theme established by the planet's name. Slowly, as we drift onward, we can think about what it would be like to approach Neptune in a spacecraft, watching as the planet grows from a distant point of light to a visible disk and then to a world that fills your view. The deep blue color would become more apparent, a rich azure that covers the entire planet in its serene shade. The clouds would come into view, bright wisps against the blue background, drifting slowly across the face of the world. The rings would appear as thin dark arcs, barely visible unless seen edge-on with the sun behind them. Triton would be visible as a bright crescent, its frozen nitrogen surface reflecting the faint sunlight. If you were to descend toward Neptune's cloud tops, you would pass through the thin upper atmosphere, where the pressure is low and the temperature is extremely cold. The methane in the air would become visible as a faint haze, and deeper down, you would encounter clouds of methane ice crystals, the bright white features that stand out against the blue. Descending further, the atmosphere would become denser and the pressure would increase, and the blue color would deepen as more methane surrounded you. Eventually, you would reach levels where the atmosphere transitions into the ice mantle, though the boundary would be gradual, a slow change from gas to liquid to exotic high-pressure ices. The interior of Neptune remains mysterious because we cannot see inside the planet, but models based on gravity measurements and other data suggest a structure similar to Uranus, with a possible small core of rock and metal surrounded by a thick mantle of compressed ices, water, methane, and ammonia existing in high-pressure states. Above this is the atmosphere, a layer of hydrogen and helium with traces of methane and other compounds. The heat that Neptune radiates comes from the slow release of gravitational potential energy as the planet contracts very gradually over time, a process that will continue for billions of years. The atmosphere of Neptune is layered, with different altitudes having different temperatures and compositions. The highest clouds are made of methane ice crystals, frozen particles that form when methane gas condenses in the cold upper atmosphere. Below these are layers where the temperature and pressure are different, and other compounds may condense into clouds, though these deeper clouds are hidden from view by the upper layers. The layering creates a structure that affects how heat and materials are transported through the atmosphere, influencing the weather patterns and circulation. Another gentle detail is that Neptune's orbit is nearly circular, with only a slight eccentricity, meaning the planet maintains a relatively constant distance from the Sun throughout its long year. This circular orbit, combined with the tilt of Neptune's axis, creates seasons that are similar in concept to Earth's but much longer in duration. Each season lasts about 40 years, a period during which the angle of sunlight slowly changes, affecting the atmospheric circulation and cloud patterns. The seasons are subtle because the sunlight is so weak and because Neptune generates its own internal heat, but they are still present, adding another cycle to the planet's slow rhythms. The study of Neptune from Earth continues with modern technology, using large ground-based telescopes and space-based observatories to observe the planet in different wavelengths of light. Infrared observations can reveal clouds and atmospheric features that are invisible in visible light, showing bright spots where the atmosphere is slightly warmer or where material is rising from below. Observations over many years have shown that Neptune's atmosphere changes slowly, with features appearing and disappearing, the overall pattern shifting in response to seasonal changes and internal dynamics. If you're still awake, that's perfectly fine. These gentle facts about Neptune continue to flow, each one a small piece of information drifting past quietly, asking nothing of you, just offering calm observations about this distant ice giant. Neptune represents a frontier, the edge of the classical solar system, the last of the major planets before the realm of small icy bodies and dwarf planets begins. Beyond Neptune lies the Kuiper Belt, a region of space filled with countless small objects, remnants from the formation of the solar system that never accumulated into a planet. Some of these objects are quite large, like Pluto, while others are smaller, ranging down to tiny fragments just a few feet across. Neptune's gravity influences these objects, creating gaps and concentrations in the Kuiper Belt, shaping the distribution of material in the outer solar system. The existence of Neptune and the other giant planets played a crucial role in the formation and evolution of the solar system. The giant planets formed early, gathering up most of the gas and ice in the outer solar system, and their gravity influenced the distribution of smaller bodies, scattering some inward and some outward, creating the structure we see today. Neptune may have formed closer to the Sun and migrated outward to its current position, pushed by gravitational interactions with other planets and the disk of material from which the planets formed. This migration would have had profound effects on the rest of the solar system, scattering Kuiper Belt objects and influencing the orbits of the inner planets. Triton's retrograde orbit suggests it was captured by Neptune during this early period of planetary migration, when interactions were more common and when Neptune's gravity could have pulled in a large object that was passing nearby. The capture of Triton would have been a complex process, requiring specific conditions to occur, and it likely disrupted any moon system that existed around Neptune before, with previous moons being scattered or destroyed by the gravitational influence of the massive new arrival. Another quiet detail is that Neptune, despite its great distance from the Sun, receives enough energy from its own interior to drive atmospheric circulation. The internal heat, combined with the weak sunlight, creates temperature differences that generate winds and organize the atmosphere into bands and zones. This self-sustaining circulation means that Neptune's atmosphere is more active than it would be if the planet relied solely on sunlight for energy, creating a world that is dynamic and evolving even at the edge of the solar system. The magnetic field of Neptune, with its tilt and offset, creates a magnetosphere that is asymmetric and complex. As the planet rotates, the magnetosphere wobbles, creating variations in the magnetic environment around Neptune. This wobbling affects the radiation belts, the regions where charged particles are trapped by the magnetic field, and it influences how the magnetosphere interacts with the solar wind. The structure of the field may be related to the way the field is generated, possibly by electrical currents in the ice mantle rather than in a central core, though the exact mechanism remains an area of active research. Slowly, the description moves toward a close, thinking about Neptune as it exists now, a distant world orbiting the Sun at the edge of the major planets, wrapped in its deep blue atmosphere, attended by its rings and moons, a place of profound cold and stillness despite the gentle circulation in its atmosphere. The planet continues its long journey around the Sun, moving through space with a patience that spans more than a human lifetime for each orbit, experiencing seasons that last decades, watched over by Triton in its retrograde path. If you're still awake, that's perfectly fine. These final thoughts about Neptune are simply here, drifting past like the planet itself drifts through the outer solar system, a quiet presence at the edge of our planetary neighborhood, far from the Sun, a world that exists in its own slow rhythm, turning peacefully in the dim light. Neptune is a reminder of how far the solar system extends, how diverse the worlds within it can be, and how much we have yet to learn about even our own cosmic neighborhood. The planet shows us that even at great distances, where sunlight is faint and warmth is absent, there can still be beauty and complexity, atmospheres that circulate and moons that erupt with geysers, rings that circle and magnetic fields that stretch out into space. Neptune represents the outer frontier of the classical solar system, a boundary beyond which the character of objects changes, where small icy bodies replace the great planets, where the Sun's influence grows weaker and the cold of deep space becomes dominant. The planet continues to orbit in the darkness, its deep blue clouds reflecting the faint sunlight, its winds flowing steadily through the thin cold air, its rings circling in their narrow bands, and Triton moving in its retrograde path, a captured world slowly spiraling inward toward an eventual destruction that will not come for millions of years. The magnetosphere surrounds the planet, wobbling as Neptune turns, and the internal heat continues to rise from below, driving the gentle circulation that organizes the atmosphere into its subtle patterns. And so the description of Neptune comes to a gentle close, not with fanfare or excitement but with a quiet acknowledgement of the planet's existence, a distant world that continues to turn and orbit at the edge of the major planets, wrapped in its beautiful blue atmosphere, a place of profound distance and cold, yet still a world, still a planet with its own character and beauty, still a part of our solar system even though it exists so far from the warmth we know. Neptune drifts through space in its own quiet way, patient and serene, existing in the slow rhythms of the outer solar system, far from the Sun's embrace, a peaceful presence in the darkness, turning slowly, peacefully, in the eternal silence of the cosmic night, a world that has been there since the solar system formed and will remain there long into the future, orbiting steadily, a blue jewel at the edge of our planetary family, a reminder of the vastness of space and the quiet wonders that exist within it, far from our daily lives but still connected to us through the bonds of gravity and the shared history of our solar system, a distant world that asks nothing of us but rewards our curiosity with the beauty of its color and the mystery of its distant realm, turning slowly, peacefully, at the edge of the known worlds, a frontier that beckons to future explorers, a place of stillness and cold beauty. Existing quietly in the outer darkness, Neptune, the farthest major planet. Drifting peacefully through space.